Okay, so I think I have patched the homework, right? So please check the homework, and we may have some discussion on homework, maybe this Thursday. So my plan, I think just finish off the Laplace, the necessary sections. So we are now having the convolution theorem. I think after Laplace, we can go directly to the matrix, but we are going to focus on the eigenvalue problem. So I expect you to have knowledge about matrix. So if not, then maybe I'll prepare something like a short video just to prepare what is matrix, some property of matrix, how to take the inverse, determinants, Cramer's rule, and so on. Because on our course, I think we only have for the matrix part, we only have the eigenvalue and eigenvector. We are going to focus on that, and after that, we are going to move on to the line integral. If we still have like time left, then the surface integral. So line and surface integral. That will be the last part. But I think before that, so by today I will finish the Laplace and maybe a little bit introduction on matrix, the eigenvalue and eigenvector. That will be really short. This Thursday, maybe some review. Maybe we can discuss some works on your homework, but not necessarily the homework, but maybe some typical problems like your homework. That will be this Thursday. And next week, on the Thursday class, we might have a quiz on the Laplace. Quiz on Laplace. So yeah, I think we can finish all the necessary chapters. Yeah, the 1 hour class. The 1 hour class, that will be a quiz for the Laplace. Okay, I think we can start the starting from this convolution theorem. Okay, so what convolutions in our case? What's so special about this convolution? Okay, so remember, when we have this asterisk like this, like form or shape, we call this a convolution. So F convoluted with G, so we write F convoluted with G. So if we take Laplace of that convolution, we can separate each functions or each Laplace. Okay? We can separate this convolution become each Laplace of each function. Okay? That's why it's so special. So we can take that and make each functions transform. So there are necessary proving point for this theorem. Let me write in the next page. So let the capital F is a Laplace of the function, right? And let this Laplace define as the integrations. And let me use another variable tau. Okay. And then another functions G. Similarly, we have, but now I will use different variable, let's say beta. Okay, so if we multiply this capital F with capital G, So we are going to multiply both integrations. So let me write these integrations. I think we can just copy to make it fast. Okay. And then if you remember the double integral, we can write this in double integral. Or maybe let me just directly add the power. So this will be negative s and then tau plus beta, and then f tau and g of beta, and this will be d tau and d beta. Okay. And we can rearrange the f tau and the tau, and then the other part will be the d beta. So this will be written like this with g of beta and d beta. Okay. Let the tau fix, and then let t equal tau plus beta. So because we let the tau as a constant, we are going to have dt equal d beta. Okay. So exchange all the components, necessary components, with dt. So we are going to have this is f tau d tau, and this will be tau to infinity e. So change all tau plus beta into t, and then beta is t minus tau, and then d beta becomes dt. To make our change of order make sense, maybe you could look at this this graph, right? So this is how we could imagine if we are going to change the order and we are going to look at the relations between t and tau. Okay. So when we move our points from 0, let's say we are going to move to the right, at some point when tau is changing from 0 to t, you see that we have this notion here, and then we are going to change from tau to infinity. So that's when we have the constant. Okay, we have the constant. So let the tau as the constant. So this is very important assumption that the tau needs to be fixed. Okay, and then we know also that the f and g need to be piecewise continuous on the interval from 0 and of exponential order. This is a must in all Laplace. Need to be piecewise, and there need to be exponential order. So we are going to set the equations. Now we are going to change the order. We're going to change the order. So we are going to change the order. The dt will be in the front. Okay. So at the beginning, we look at the tau from 0 to infinity, okay? And then we shifted in, I hope you still remember the double integral. So we shifted, so from, this is tau, so tau is from here, from 0 to infinity goes up there. And we shifted to become dt at the first, so we are going to let the t move from this point to this point. So that's why we are going to have from 0 to infinity. And then the tau itself will be from 0 to t. So this part, the shaded area in the double integral. This is actually similar, very similar with the, if you remember the double integral, changing the order, like dx dy becomes dy dx. Okay? Well, you can open your notes later if you don't remember. Okay. Okay, but we changed the order. And then we are going to look at this. And this is pretty much, so let me write here. So if you look at this, and we could write, okay, we could write all this here. So it's like a Laplace, right? So if you have e with power of negative st, and let this as a function. This is a function of t, right? So this is the same as e with power of negative st, f of t. So we are going to have Laplace of this function. What is this function? This is the convolution. Right? Convolution that we defined, I think, in last week. So we can, this is convolution. F asterisk g. So we could write down this is equal to Laplace of the convolution f and g. Okay, I think Laplace, if you remember, if we have this, we are going to have this. Okay. So whenever we find functions that we could see that we have like similar structures like this, we could directly write this f convoluted with this t. And if we have this part, then we just take the Laplace of this convolution. Example, let's say we have Laplace of integrations from 0 to t, e with power of tau, sine t minus tau d tau. Okay. Now this is pretty much the same structure. We have e and we have sine, so two different functions. So f, and then g will be the sine. So we know that this will be e convoluted with the sine. Okay. So we could say that we could write down this as Laplace okay, and then we could take this as Laplace of each functions and multiply. Okay. Now, of course, every Laplace will have an inverse. So we could also take inverse from this convolution. Okay. Okay, but I think the important point in our convolution is whenever we have Laplace, and we know that the inside will be a convolution, then we could separate, become each Laplace and multiply. So Laplace convolution fg becomes Laplace of f multiplied with Laplace of g. Okay? Okay. This is to prove that this is true. And then another theorem is for inverse. So if we have Laplace inverse of the f as gs, this will be the f convoluted with g. Okay. As simple as that. Okay. Okay, let's see the example. Let's say we are going to evaluate Laplace inverse of 1 over s squared plus k squared and then squared. Okay. So the first step is to identify our f of s and g of s. So f of s and g of s seems the same to 1 over s squared plus k squared. So we imagine that there will be a sum multiplication inside here, which consists of f and g. So that's the first step. Identify f and g. So we identify that the gs or f of s, they are the same value of 1 over s squared plus k squared. Okay. Now because of this, we could imagine what kind of inverse from this part that we have for f of t and g of t. So if you have s squared plus k squared in the bottom, then perhaps this is constant, perhaps it will be a sign, but we need to multiply with the constant, okay? Because this is k squared, so we need to multiply with that, right? So this gives the f of t equal g of t equal, we could write 1 over k and then Laplace inverse of k over s squared plus k squared, okay? Or we could say that this will be sine kt over k, okay? So that is our f of t and g of t. And now the Laplace inverse of the questions, right? Now we are going to write the convolution part, okay? The convolution part. So f g, this part here, we are writing the convolutions f convoluted with g. So we are going to write with some integrations, f and then g and then with t minus something like that, like the previous section. So we are going to write, and since they will have both f over k, we are going to multiply f and g. So we have 1 over k squared for this one, because we have this squared here, right? So we are going to have 1 over k squared and then the convoluted part. Or maybe let me write to make it more feasible. Let me write or maybe directly just write directly. So this will be the convolution 0 to t. This is sine kt and sine, or maybe tau to differentiate, sine k t minus tau and then dt. Now we need to solve these integrations. So we have a problem because we have sine multiplied with sine. So we need to rewrite the trigonometric part. So sine we can rewrite becomes cosine minus cosine. Right? Okay, do you remember? Let me write for you. So sine A sine B is half cosine right? Okay, why we need to write like this? Because if we write this cosine minus cosine, it's easily to be integrated, right? So sine, we are going to write with, using this equation. So cosine A minus B. So let this A, this B. So let me write for you. So this will be, so half will be going outside, so it's 1 over 2k squared, like that. And then same integral, 0 to t. And then this will be cosine k. So minus, so plus 1. It becomes 2 tau minus t. And then minus cosine. Adding both sides, the tau will be cancelled, so we are going to have kt. Okay, and we need to integrate this with respect to and then finally integrate each of this. So 2 tau becomes 1 over 2 k sine k 2 tau minus t minus tau cosine kt from 0 to t. And then just substitute t inside and zeros on the side. So this will be 2k cubed and sine kt minus kt cosine kt. So this will be the Laplace inverse of 1 over s squared plus k squared squared. Okay, 2 more sections on Laplace, and we are going to finish Laplace. Okay, so from the convolution part, imagine that if we let the g of t is 1 and Laplace of g, this is become 1 over s, right? At the very beginning, right? So, if you take Laplace of the integrations from 0 to t f tau and d tau, we could simply, so because g, we let g is this 1 inside here, so we could take that g as 1 over s. So we could write down this Laplace as f of s over s, okay, if g is 1. Okay. So we could simplify the convolution theorem if we let g or f is equal 1. So we could say that we are going to define the f of s with s. Our usual convolutions, we usually have f and then g, t minus tau, right? And and that part is equal 1. So instead of f multiplied with g, we multiply with over s, because we know that the Laplace of g is 1 over s. Okay? Let me write here to make it clear. Okay. Previously, we know that if we have Laplace, we have convolutions, we are going to have this, right? And this is equal to f of s, g of s. Okay. Now our g and these terms are supposed to be having integrations f and then g, but g is a constant one. So we just need to define the whole thing, the f with s. Okay, and then we could also take the inverse. So integrations this too. So this is the inverse form. So for the inverse part, whenever we could identify that some functions is defined with some s, then we could take this with this theorem. So if we take let me check. So let's say we have example Laplace inverse of 1 over s and then s squared plus 1. Okay. Now we could imagine that this can be identified as 1 over s squared plus 1 divided by s. Right? So we could write this into this form. So 1 over s squared plus 1 divided by s, right? And this part, 1 over s squared plus 1, you could identify this is sine, right? So we could write this as a sine. Then this will be integration from 0 to t sine tau d tau. Okay. And simply we solve the integrations and the solution is 1 minus cosine t. I know becoming more. I think the beginning Laplace until the middle part, at least solving the normal differential equations should be familiar enough. But I think from the middle part until the convolutions until here, it's a little bit rough. So you need to be careful on this part, especially I think since from the translations, the unit step functions, and then the convolutions, and then after this we have another part that is similar to unit step function. We call the Dirac-Delta function. That will be the last part, and then it's quite difficult to teach. There is one more Volterra integral function, but I will skip that part. I will directly go to the Dirac-Delta function. Okay, let me write another example because it's quite interesting. If we let the inverse, okay, and then we just add multiplication for the s, so s squared plus 1. Okay. We could let this, it's actually similar with this, but we divide with 1s, right? So it's the same thing as this part, but we divide with s again, right? And it's becoming x squared. So we could say that the result will be the integral of this. And if we divide with 1s, we are going to integral the result of this. Okay, so let me write here. So this is going to be 1 over s squared plus 1 divided by s, right? And we already defined this solution, that is this solution. Okay, so we could write again the integrations of this 1 minus cosine. Now need to use the dummy variable tau to compute, and we are going to have t minus sine t. And the same thing when we define with x again becoming x cubed, then we are going to take the integration of this. Okay. Okay, any questions? I think as long as you get to know this two formulation, I believe it will be okay. So actually, what our goal in our course is basically the first part of our goal is to understand the differential equation. By that means, it doesn't mean that you are going to know everything about differential equations, but this course is just to get you familiar with the differential equations. So whenever you see one equation that you know that this will be differential, then you can think from some methods to solve, even though not really maybe mastering all the methods, but you know what's the principality of the finding the solution. Because I think differential equations will be applied within many subjects, especially when you deal with simulations. And although you are dealing with mostly using software, but understanding how the software works and how they are solving the problems is actually, I think, it's really important. Because I believe that if we learn the fundamental part of the course, that will be more important than the applied knowledge. Applied knowledge, you will know when you experience with with the first-hand experience. You will know directly the practicality. But fundamental knowledge is different. You need to understand the knowledge first before you go to the practice. So even though you are not really deal with any practice or any real world problems yet, but you know the fundamentals. That will be the core essentials part. Okay, let me move to the new slide. So this part, we are going to take you to the functions that call the Dirac delta function. So obviously, Dirac is the name of the person who finds, and the delta is the delta like you deal with the symbol delta in the Greek letters, and sometimes the delta symbolizes the difference or the gap. So what this functions means, or how we deal with this, is sometimes in some phenomenon, if you have learned the electricity, imagine that electricity is not as stable as you think, right? Sometimes it has a sparks, like in some split of seconds, it should be like it jumps from 0 to some high point directly, right? When you are dealing with the maybe when the lightning strikes your body. Don't imagine that, but yeah, it seems that you will have like high voltage, right? From 0, and suddenly it's peak. It goes to peak, right? But it's happening in a split of seconds. So sometimes in the real world, there will be some phenomenon that in a split of seconds, the function will be going to change drastically. Okay? So that's what we are going to observe. So first, we deal with we call the impulse, the unit impulse. Or maybe you struck something like in the boxing, you box with your opponent. If you can perform some movements that is in a split of seconds, suddenly impact your opponent, and maybe that is the one way to knock out your opponent, right? Maybe you can think of that. But don't do that at ease, okay? Don't do that to your friend. So let's say we have these functions. So let's say we have an interval. We have this interval. And imagine that we have this, let's say it's like all this interval. And we could write the graph when the phenomenon happened, maybe like this. So as A getting closer to 0 or getting shorter and shorter, we can see that from this behavior that when we are going to have that, means that at the t0, if we let this as our delta, the delta A, the split second of A, we see that it has huge, significantly increase. Right? Now this we can write, or maybe let me put here so that I can write on the sides. So the delta between this interval, so it will be 0 from t until t0 minus a. It means it's going to be here, 0. And then it will be equal to 1 over 2a. That is the length of this part, okay? This is t0 minus a less equal t less t0 plus a, and then becoming 0 again when t is greater than t0 plus a. So we have this 1 over 2a when it has a sudden impact. and then this is A need to be positive, T0 also need to be positive. So we need to also imagine that this is very short, okay? Very short period. This is unit impulse. Okay, we are going to take a break and we will continue after the break. Okay, so back to this Dirac delta. So I forgot to mention that the behavior of this Dirac delta functions when you are approaching this T0 from the left and the right, the more you get close to T0, the value is getting higher and higher and higher, and somewhat going to have an infinite points. So we could write that at the t equal T0, but aside from that, we are going to have 0. So it's going to be like from 0 here, when we get close, from here, okay, get higher, okay, and then we get close again, okay, so getting here, and we get closer and closer and closer, it's somewhat getting this peak, okay. So when we have like getting close, but it's not going to be equal directly to the T0, well, it's getting close. And because we are dealing with this approximations, we are going to deal with the limit. So we take the limit for this definitions. So this is the limit as A getting close to 0. Okay. Okay, another property within this Dirac delta, if you let's see here. So there is a reason why we have this 1 over 2a and 2a. The reason is when we deal with the area under the curve, from this part here, we're going to have 1 over 2a multiplied by 2a is equal 1. So the integrations of this area will always be 1. Because when you get closer, it's getting higher. And you're getting closer, and getting close to T0, the y-axis will be really high, and the delta x is really small. But the area is still 1. The multiplication is still 1. Okay? So, the second property is that, let me write here, A, B. The second property here is the integrations of this delta is equal 1. Okay. Okay. Now, to transform this Dirac delta, let me write the definition first. For the T0 that is positive, the Laplace of the delta or Dirac delta is equal e with power of negative s T0. So let me begin with these definitions and let's see how we can prove that. Okay, so we begin with to prove this, we begin with this part. Okay. Remember when we have the unit step function, we can write unit step functions and taking this t0 minus a for this part and t0 plus a for this part. So this will be t minus t0 minus a, and we have the unit step function. So we can write the unit step functions. So we can write here the unit step functions t minus t0 minus a minus unit step functions t minus t0 plus a, and we need to multiply with 1 over 2a, right? Because we start from here. In the normal unit step function, it's 1, right? We just multiply 1. But now we have the 1 over 2a, so we need to multiply with that. So we could say that our unit step functions form of this graph is that equation. Okay, so we could write, let me copy that and write here, let me copy here. Okay, so this will be the delta of delta a t minus t0. Okay, let me change everything from this unit step functions by using the transformations. So taking Laplace, so Laplace of the delta a t minus t0 this will be 1 over 2a, this is just a constant, and unit step functions is e to the power negative s t0 minus a, okay, and then divided by s, and then minus e negative s t0 plus a, and then divided by s. Okay. And then e with power of negative s t0, let me factor out. This will be e sa minus e negative sa. Okay. Let me maybe bracket more bigger, and then put inside 2sa, and then we know that the Laplace we are going to put the limit sa getting closer to 0 of Laplace so this will be e power negative s t0, and then limit sa getting closer to 0, and then all these equations we are going to write. So if we take 0 inside here, substitute a, this will 1 minus 1, 0, right? This is also 0. So 0 to 0, limit, L'Hopital rule, derive, you will have at the end, because this derivative of this is 2x, so you can say it's a constant. So something have variable, constant, and you will see that this e will be minus with this e, this will be a 0. If you divide separate, maybe 2 times derive, you will get it 0. Not 0, it's 1. So this will be equal to e negative s d0. So when d0 is equal 0, then we might have the Laplace of the delta t is equal 1. This is a little bit different from the theorem that we have learned before, that previously when we have Laplace, when we have 0, s will be getting infinite, right? Because it's getting over s, right? So now the Laplace is getting to equal 1. Yeah, I think this finish. Let me just write one example, and maybe we can move to another subject. So Dirac delta, whenever you see the symbol is having a delta like this, it means that it's in Laplace. This will be considered as a Dirac delta. Okay, let me give you an example. So now in differential equation, when you see delta like this means it's the Dirac delta. So first is we need to start from taking Laplace of this differential equations. Let me write. Okay, we start from the y double prime. So we are going to have, remember, s squared capital Y of s minus s, right? And then all the things is y0, so we will write here y0 and then minus y prime 0, right? And then plus. And then the 4 delta, this will be 4 as constant. The delta will be e with power of this 2 pi, the negative 2 pi. E with power of negative 2 pi s. This is 0, this is 1. So we have s squared so we say that we are going to solve okay. So my expectation is you need to be familiar with the partial fractions and everything to solve this algebra parts, because I think mostly we are going to depend on this very much, okay, for this part. So if you feel maybe you are not really familiar, I'm suggesting to have more practice, okay. Okay, and then we take the inverse and getting the yt. So this will be cosine. And this going to be, we can see this part as, let me write here. So 4, and then you have 1 over s squared plus 1, and you have e negative 2 pi s. Okay. So this is good. This could be sine, right? This is sine, and you have e. But probably you have the unit step function, and then you have e minus this a is negative 2 pi. So this will be. Is going to be sine t negative 2 pi, and then unit of function t minus 2 pi. Okay. So let's write 4 sine okay. But this equations we could write in more precise. So because that's sine t minus 2 pi, this is still equal to sine t, right? So the solutions we could write so from 0 to 2 pi, this will be cosine t. And then this will be, the other part is cosine t plus 4 sine t. This is when t is greater than 2 pi. So what does it mean? So this equation gives you this piecewise. Okay? So you could imagine cosine as a simple harmonic periodic function, and then after 2 pi, it's getting plus 4 sine t. So it's getting plus, so it's getting like, right, so maybe take the graph. So let's say this is cosine up until there. This is 2 pi, this is 0. And from this 2 pi, you get some additional motions. Okay. Okay, now try the same questions with different restrictions on the initial value problems. Okay, okay, solve the same thing. So solve. And now this is the initial value. It's a little bit different, but let's try. Okay. This will be s squared. Let me copy. And now this will be 0, this will be 0. So we are going to have or this y-axis is 4e divided by s squared plus 1. Okay. Now what does it mean? This is going to be directly if we write yt, let me make this a little bit higher right here. Now then this will be equal to 4, and then this will be sine, and then unit step function. So sine t minus 2 pi, unit step functions t minus 2 pi. Okay. And the same thing we can write in a piecewise definition. This will be, now we take 0 to 2 pi. Now it could be 0, right? It could be 0. This sine could be 0 when it's 2 pi. So we could write, it could be 0 for 0 to 2 pi. And it could be 4 sine t when you have t is greater 2 pi. So now it's a little bit different. Now the graphs become so it's going to be from 0 to, let's say 2 pi is here. It's going to be 0. And then from this 2 pi, we're going to see 4 sine t. Okay. So it's no motions for this one, and from 2 pi gets the harmony. While in the first one, it's already being a harmonic, but then added with additional value. questions? So now we have, aside from the unit step functions, that is like u like this, the curve u, and now we have the delta. So I hope you get the point. Can you get the point? So unit step functions is when you have some part of your interval multiplied by 0, because it's like switching on and off. So 0, 1, 0, 1. I think that's the unit step function. But the delta is a little bit different. The delta is when we are going to get close to that particular interval, we are going to have a significantly peak. The peak will be significant. Like when you are like boxing, sometimes your punch really have a sudden impact, or we call it in mechanical, the load is called the impact testing, sudden impact. Yeah, I think in mechanical there's terms of impact. So you have dynamic testing. You have the impact. I think maybe you have learned like we have the tension testing, right? The torsion, no? Torque, right? Torsion, bending, you know bending. I think in statics or maybe yeah, bending. You have like maybe 2 points bending like that. And what else? And you have impact load, impact testing. Impact testing is, well, usually you have like a cantilever and then like a pendulum, and you are releasing those loads, boom, and it has like a sudden impact. And then the tensile testing, no? Still not correct. Yes, correct. Yeah. Although there is basic mechanical testing for basic mechanical testing. Okay, now the next part, I will move to the matrix, but I will just list what you need to know beforehand, okay? So you can maybe take a review. So the next part is a matrix. So first, of course, the matrix algebra. I hope everyone familiar with this. And then system of linear algebra equations. Just the basic one, not the real linear algebra, which is different courses. And then the determinants. And an inverse of matrix, which involving the determinants, if you remember. The Cramer's rule. Yeah, I think this 5. The system of linear algebra, it include the Gaussian eliminations, the Gauss-Jordan elimination, or Gauss eliminations. The row echelon form, right? Row echelon system. You remember that we need to make it 1, 1, 1, 1. Explain to I think basic math. If you take basic math with me, I also explain that. But I do hope this 5 you are able to familiar with. Maybe I will add some information additional information about the second part, how to solve a system of linear algebra, which we call sometimes Gauss elimination or Gauss-Jordan elimination, or we simply just call the row echelon form. But simply we are just reforming all the system of linear equations into a matrix, and then we need to solve the matrix. We are taking basic operations like plus, minus, multiply with constant, divide with constant, but we are doing it in a system of row. So row by row, we are going to multiply, we are going to add, subtract. I will show you later. Just an example. And then the other part, I hope you get to know by yourself. Maybe before that, maybe among these 5 components, which part that you are no clue? Which part? You still have no clue about that. All? No. Everything? I think matrix algebra okay, right? Matrix algebra is you have matrix A plus matrix B, and then you can plus, okay? And then if you multiply the matrix, what will happen? And then, well, you need to know that if we multiply the matrix with its inverse, we are going to get, yes, I did. Yeah, if you take matrix A and then multiply with matrix of A inverse, result will be identity. Okay, point. Okay, perhaps I will have some additional information about matrix. But I think this will be for next Tuesday. This Thursday, I think we can focus on exercise for Laplace. Grammars? Still okay? Or maybe clueless? Cramer's rule is related to determinants. Determinants, and then you substitute the column with the right side of the equation. No? Yeah, anyway, I hope I can get prepared by the time before Tuesday. I hope I can prepare the video for you. But if not, maybe I will look for additional sources that you can look up for that. Okay. But our focus is after this. Okay, we have eigenvalue and eigenvector. So we just write first, just to give notes what we are going to learn. Eigenvalue and eigenvector. Yeah, because I think the textbook itself already have a lot of content, which are consisting some part of calculus, but adding with more advanced content. And we are having, I think, up until now, just 1/4 of the book. So not yet half book. Yeah, perhaps we need to have like 2 courses for this whole engineering of math. Because the content is too much. Okay, I think we are going to end up till here. I will continue this next Tuesday, but this Thursday we are going to have an exercise. Next week Thursday, we are going to have a quiz, okay, on Laplace transformations. Okay. As usual, you can prepare your notes, A4 notes. Okay. Okay. Okay, let me go through the feedback. So feedback as usual. Hi. You get in on time for feedback. Okay. Okay, if you haven't scanned, you can go to the website menti.com and use the code 871692002. Okay, use your student ID. Well, usually we have a lot of students joining now. I think it's the same as in class. Okay. Okay, I think we can start. Okay, let's start. 3, 2, 1. I hope the time is okay. I forgot to check the time. Yeah, 4 minutes. I hope it's okay, 4 minutes. And before you calculate, you can check the you can check the restrictions. Each one. Is it equal or not? If not equal, maybe not the answer. Just checking, just checking. I think you can also look up your homework and try to check your time when you solve each question. I think one question, there is some misinformation. I will later tell you which part. Okay, the answer is B. Okay, okay. Yes, okay, second one. What the question is? I forgot. Oh yeah. Okay, I have 2 minutes. Okay. So we could start from the options and then see if it is logically okay or not. I think you can look at the last one. The last one. So I think the easy one. If you could look from the C, I think you could rule out the other three. And you can just choose in between two. Easy, right? You can just imagine plug in the value and see if it is getting 0 or not. Okay, good. Okay, good. Will be right? Good. Okay. Okay, good. Okay, attendance. So Thursday, exercise Laplace. Next Tuesday, continuing the matrix. And Thursday next week, the quiz. Chapter 4. Prepare your A4. Bring your calculator. But I think A4 is more important for Laplace. Yeah. Yeah, you can prepare before. You can prepare, so you can optimize that part. And please write the notes carefully, because sometimes you will write messy, not useful in exam. Okay, I think we stop here.